So we are looking at this integral. It looks very challenging, but it will be much simpler if we think about it in terms of spherical coordinates. So looking at the order of the variables dz, dy, dx. So this starts out as z. So what is z equals 0? That's my lower boundary, if you will, my lower wall. Z equals 0 corresponds to the xy plane. So that's my lower wall. My upper wall is z equals the square root of 4 minus x squared minus y squared. I want you to recognize here z is always positive. So as I square both sides, I get z squared is 4 minus x squared minus y squared, and we get x squared plus y squared plus z squared equals 4. Now, we said that it was starting on the xy plane, and we said that z is always positive, but this is the circle centered at the origin with radius 2. Check that, a sphere centered at the origin with radius 2. But we only want the upper half of that sphere. So if I'm drawing this picture, what am I going to get? I have my xy plane. I have the point 0, 0 here, and I have the hemisphere above that thing. So what will that look like? Radius is 2. This is where we are headed. Possibly for our region of integration. Again, lower wall is the xy plane. Upper wall is the upper half of that sphere. Now, bounce it to the left, what do we have? We have y equals negative root 4 minus x squared to y equals positive root 4 minus x squared. So what will be my region of integration? Can we have that conversation? So if y is negative root 4 minus x squared, that's only negative values of y. Squaring both sides, we get this. And then x squared plus y squared is 4. So that's the lower half of a circle with radius 2. So what would that give me? Lower half of a circle of radius 2. This is the lower part of my region of integration. But no surprise, it goes up to y equals root 4 minus x squared for the upper part. So those are only positive values of y. Y squared equals 4 minus x squared. X squared plus y squared equals 4. Again, the upper half of that circle. So this now is my first guess for my region of integration. But I need to see which x values do I use. So I finish this off by going to the last part of the discussion, where x ranges from negative 2 to 2, which would give me this whole thing, since we go from negative 2 less equal x less equal 2. So this will be my region of integration R or B. Oh, this is the region R, and this would be the region B up here that we're integrating over for our triple integral. So the upper half of a sphere of radius 2. That's what we are dealing with here. Now we've got to do some work to convert this into spherical coordinates. So let's quickly work with this portion. If I want to convert z into spherical coordinates, I need to remember the triangle. Here is z, here is rho, here is phi, here is r if you need it. And the relationship there was what? Was cosine of phi was z over rho. So rho cos phi equals z. And I need z squared. So rho squared cos squared phi is z squared. So let's keep that in mind. There's our z squared. And that's going to be rho cos squared phi. How about the next portion of that integral? We have the square root of x squared plus y squared plus z squared. But we know x squared plus y squared plus z squared is rho squared. So if I zap the square root of x squared plus y squared plus z squared is the square root of rho squared, which is just rho. So that will be our second piece here. Our second piece, rho, is right here. And then dz, dy, dx, do we recall how that's going to work in the world of spherical coordinates? We know that dz, dy, dx equals rho squared sine phi d rho d phi d theta. So that's the third part that I am going to substitute. So that takes care of the argument of the function. Now, what about our endpoints? How are we going to set up that integral? Let's consider that. So this was a hemisphere of radius 2. So that tells me that 0 is less equal to rho is less equal to. Now, how about phi? Phi starts at the North Pole, and then it moves down until it gets here. So what are my range of possible values for phi? Notice that's 90 degrees. Phi goes from 0 to pi over 2. In theta, you'll notice our circle, our region of integration was the full 2 pi for the circle. So theta indeed runs from 0 to 2 pi. So is that enough for me to set up the integral that I need here? So our endpoints are here. Z squared we said was rho squared cos squared phi. So put in rho squared cos squared phi. Root x squared plus y squared plus z squared just turned into rho. And dz, dy, dx turned into rho squared sine phi d rho d phi d theta. So what is our order? I like to go rho first. What does rho range from? Looking at our picture, rho starts at 0 with the origin and goes out to 2. Rho goes from 0 to 2. Then we do phi next. What does phi range from? Phi ranges from 0 to pi over 2. And theta on the back end, theta goes from 0 to 2 pi. So we have successfully converted this from rectangular coordinates to polar coordinates, and our hope is that this will be much simpler to evaluate. So simplifying this, we'll see rho squared gives me rho to the 5th, sine phi cos squared phi, then d rho d phi d theta. We'll do our usual things, starting with the innermost inner integral. So as far as rho is concerned, sine phi cos squared phi is a constant, which then gives me sine phi cos squared phi. The antiderivative of rho to the 5th would be rho to the 6th over 6. Evaluated as rho goes from 0 to 2, which gives me sine phi cos squared phi 2 to the 6th over 6 minus 0 over 6, which is 2 to the 6th is 64. Then reducing that fraction, and we conclude our innermost inner integral. And this is the result. So now we're going to go ahead and move that in as our innermost inner integral, which is from here to here. Make that substitution and do our inner integral. So substituting in our innermost inner integral, now we'll take a look at the inner integral, which is as follows. Let's pull out the constant of 32/3. This now requires a u substitution, so let's let u equal cosine phi. So to do the u substitution, we know the derivative of cos phi is a multiple of sine phi, so u is going to equal cos phi. So then the derivative of u with respect to phi is negative sine phi. Du d phi is negative sine phi. So du divided by negative sine phi will be d phi. But I also like to change my endpoints. So if phi is 0, u is cosine of phi. So u is cosine of 0, so that would make u 1. In the instance when phi is 0, u is now 1. And then if phi is pi over 2, same kind of an argument. U is cosine of pi over 2, which is 0. So let's go ahead and make those substitutions and see where we get. We get 32 over 3. If phi is 0, u is 1. If phi is pi over 2, u is 0. I'm going to leave sine phi alone. But cos squared phi, u is cos phi, so cos squared phi is u squared. And then d phi is du divided by negative sine phi. So we're pleased that the sine phis divide out, so the minus sign can come in front, and I get minus 32 over 3 integral as u goes from 1 to 0 of u squared du. But I don't like the fact that this is going backwards in time. I'd rather have it go from 0 to 1 than from 1 to 0. So if I'm going to switch the order, I have to multiply by negative 1, which I will do, making this positive 32 thirds. Switch the order. U goes from 0 to 1 of u squared du. Now, the antiderivative of u squared is u to the third over 3. So I get 32 over 3, antiderivative of u squared. U to the third over 3 evaluated as u goes from 0 to 1, which gives me 32 ninths times 1 to the third minus 0 to the third. 32 ninths is my inner integral. So we'll go ahead and make that substitution and finish off our computation. We were here previously, and that inner integral is 32 ninths. So let's replace that with 32 ninths. Integral as theta goes from 0 to 2 pi of 32 ninths. D theta, well, the antiderivative of that, of course, is 32 ninths theta. As theta goes from 0 to 2 pi, which gives me 32 ninths times 2 pi minus 0, which gives me 64 pi over 9. The decimal approximation for that, it's about 22.3402. And let's check that with technology, see if it's correct. So using the triple integral calculator from Wolfram Alpha that I found online, it's the dz, dy, dx order. So you see it's z squared times square root of x squared plus y squared plus z squared. That's what we're using for our function. Z is going from 0 to square root of 4 minus x squared minus y squared, again, from the xy plane up to the upper portion of that hemisphere. Y goes from negative square root of 4 minus x squared to positive square root of 4 minus x squared. And x is going from negative 2 to 2. And let's see what we get. And you'll notice we get 22.3402, but you'll also notice that Wolfram Alpha was unable to give us an exact number in the standard computation time because it's using brute force rather than trying to use spherical coordinates to solve the problem.